A really common question that occurs in cloud networking designs, and in fact in any network design, this is a problem almost as old as networking itself, is what happens if I have overlapping IP addresses with another part of my network or a network that I'm connecting to, such as a third party. So I've got the blue space here, that's my Azure, and I've got a red third party here. And we can see that their on-premises network, the IP address here overlaps with my IP address here. This is something that you hear from customers quite a lot when they set up IPsec VPNs to remote third parties, where you don't have control of how your business partner manages their IP address space, and quite often it overlaps with yours because the RFC 1918 blocks are only so big and there's quite a high chance of overlap. In this video, I'd like to talk about the options you have to use native Azure products to address this challenge, and we'll talk about two high-level solutions, one using the NAT feature on the VPN gateways and another one using Azure Private Link. Let's start with a really simple scenario. Azure on the top with a hub VNet and a native VPN gateway. Inside of the same VNet, I've got a virtual machine with this IP address here. Site-to-site IPsec VPN over the internet to an on-premise location here in red with an on-premises firewall terminating the IPsec connection. An on-premises subnet here with a virtual machine with this address 172.16.100.4. Okay, so I've pre-configured everything here, so we have reachability, and just to prove that, I've logged into the blue virtual machine here. You see we've got the right IP address 172.16.1.4. And let's just make sure I can ping my on-premises virtual machine, which I can. So everything's happy at the moment. I've also got a connection open to my on-premises VPN device here, and you can see I've got a BGP peer online, which is my Azure VPN gateway. And at the moment, if I just check what routes I'm getting from that peer, we'll see I'm getting the prefix here for the VNet, the hub VNet. I'm also getting one additional prefix that happens to be the P2S pool configured on that VPN gateway. So that's not related to this scenario. Okay, now I've updated my lab. I've created a spoke with the same IP address prefix assigned as I've got on premises, and I've peered that to my hub. And we can see this is going to be problematic from a network point of view, because how can I virtual machine with the IP address on-prem of 172.16.100.4 route traffic to a VM in Azure that's got the same IP address? The virtual machine has got no idea and any conceptual way of routing that traffic. We can also see here that since enabling this additional VNet peering inside of Azure and ticking the box for user remote gateway, the VPN gateway now is advertising out via BGP to my on-premises device this subnet range up here. And we can see that reflected over here. And I rerun the show BGP routes command for my peer. So this is from the on-premises firewall. I'm now getting this particular subnet. And this is no doubt going to confuse the on-premises device because it's now seeing the route from BGP, and it also knows about the route locally. There's a route on the on-premises device saying to get to the local subnet, go out of your inside interface. So even though it's receiving it via BGP, it's not actually inserted into the routing table. And you can see that in the output of these commands here. You notice this hasn't got a right-hand pointy arrow next to it. And if we do a show IP route for that specific prefix, you'll see that it's pointing out of the local interface on the firewall. Before we jump into our first technical solution, I want to clarify the scope and direction of the video. What I'm going to focus on here is the scenario where your third-party B2B partner wants to get access to a specific application inside of your virtual machine wherein they initiate the traffic. I also want to clarify a second point, which is I'm not talking here about stretching your layer 2 subnet from on-premises into Azure and being able to maintain the IP address of your VMs as you move them into Azure as part of a cloud migration, which is also a common request. And that's better served by technologies such as HCX, which runs on top of VMware. And you can look to leverage that if you make use of Azure VMware solutions. Before I get into configuring solution number one, I did also want to show you the BGP status on the VPN gateway in Azure. So the VPN gateway here in my hub VNet, over here on the right hand side, down to BGP peers, we can see that we are receiving this prefix here from on-premises. So on-prem is advertised in the client subnet within which my VM sits into Azure. However, naturally, if I go to my VM in the hub and see how it views the world of this address space, the 172.16.100 address space, over here on the right hand side, we can see that as expected, it sees the route via VNet peering. Why is that? Because we connected that VNet with the same address space. So even though my VPN gateway is getting the route from on-prem, it's not able to inject it into the Azure SDN because there's a local route via VNet peering, which obviously wins. Okay, so solution number one is going to involve using the relatively new feature of NAT on the VPN gateway connections. This is now fully available in a GA state. I'll leave the link to the article here about how to configure it. So I've gone into my VPN gateway here and I've configured two NAT rules. Let's take some time to understand what's going on here because this can be fairly intricate. So we've got one inbound, one outbound, both static NAT rules, ingress NAT and egress NAT. So on the inbound, I'm taking this prefix, the one that I know overlaps, and I'm telling the VPN gateway to remap it to 200.0.0.0/24. On the outbound, I'm taking my subnet, which we know overlaps, and I want the VPN gateway to represent it as 100.0.0.0/24. So on my diagram, the logic looks like this now. When traffic leaves my VPN gateway, sourced from this subnet, 172.16.100.0/24, remap it to 100. So I would expect my on-prem site to see traffic and be able to reach my backend application on the 100 subnet. In the opposite direction, if my VPN gateway receives a packet from the on-premises network from that overlapping block, it's going to rewrite it to 200, which means that if my on-premises network was to initiate a connection into my application, I would expect to see it coming from this 200 block. One of the things you have to do is to associate these NAT rules with your connection, and you notice I've also enabled BGP translation, and I'll show you the effect of that in a second. So on my connection here, I went into NAT rules and I set the appropriate setting here. So the importance of ticking that enable BGP translation to yes, we can see that by going back onto our on-premises firewall. And notice now when I run the command to show the received routes from Azure, it's not actually getting a route for 172.16.100.0. It's getting a route for 100.0.0/24. So the impact of that NAT rule is that it also influences the BGP advertisement, which is exactly what you want, because the on-prem network now is receiving a unique IP address from Azure, which it can make use of and inject into its local network without an overlap. What's also interesting to observe is that if you look in the effective route table of a VM in the spoke or a VM in the hub, as you would expect, if you think about the packet walk, they also learn a route to the masquerading IP address of on-premises. As we said, the VPN gateway is making on-prem appear as a 200 range. And if you look in the effective routes of a VM in Azure, you see that it thinks that to get to the 200 range, it should go to the VPN gateway, which of course you need for the Azure stack to process the packet. It's also worth noting that in the VPN gateway on the Azure side, in the BGP routes, we can see here that after the NAT config, we see the inbound NAT rule taking effect here in the learned routes. So the $1 million question is, after all that configuration, does it actually work? So here I am on the left-hand side on my on-premises red virtual machine with the IP address 172.16.100.4, I now would expect to be able to enter Azure and obtain the application, a simple web service running on this Azure VM on the NAT address that we talked about. So I'm going to target the 100 range, which is what my VPN gateway is transposing that internal subnet to masquerade as. The first thing is, can I ping it? I can, that's a good start. Can I browse to the website? Answer is yes. A very simple Apache web server running on that backend VM. Just to confirm that further, here I have a SSH session open on my web server in Azure. And as we said before, we would expect to see packets now coming from red to appear as if they're coming from the 200 range. So the VPN gateway is making my external third party masquerade as that 200 range when it hits my web server. So let's confirm that is happening. I've set up a very simple packet capture on the web host, looking for any traffic from the address which I know my on-premises site will be netted to. I'm going to refresh my attempt to browse that server, and we'll see we're getting packets. If we look at one of those packets, we can see it's traffic coming from 200.0.0.4 going to the web server. So what is the net outcome of what I've achieved here? Ultimately, I've been able to say to my remote third party, if you want to access my application, make sure you target it on this 100 range, a range that I know is unique to you. In the opposite direction, for the people that own my application inside my spoke, I've said to them, hey, when you get traffic coming from this third party, this red third party, it will appear as this 200 range. What I haven't had to do is tell either my internal application team or my remote third party to change the IP addressing which they're using on either the client or server. So that's the value proposition of handling it on the VPN gateway. As the central IT team in the blue box, I've been able to do the entire configuration stack required to get this end-to-end flow working using logic inbound and outbound on the VPN gateway. Let's try and really bring our understanding home now and do a full packet walk from the remote third party into our backend web server in Azure. The life of the packet starts off on my on-premises virtual machine with the source of the VM itself, 172.16.100.4, destined for 100.0.0.4. My on-premises network needs to be configured to know how to route traffic destined for that network. My on-premises network will need a route saying any traffic going towards that 100.0.0/24 block, send it to the VPN appliance. When the VPN appliance gets the packet, it's with this information here. So sourced from 172.16.100.4, destined for 100.0.0.4. My VPN device needs to know I should send traffic destined to the 100 range inside of that IPsec tunnel to Azure. In our case, how does that happen? Very simply, on our VPN device, if we do a show IP route for that destination, we see that it's known via BGP. The next hop is this address here, which is the other end of my BGP session on my VPN gateway in Azure. VPN device on-prem puts the packet on the wire inside the IPsec tunnel, travels across, and it enters my VPN gateway. So the packet comes in, sourced from 172.16.100.4. What should my VPN gateway do? Well, there's an inbound rule saying, hey, any traffic from that range, transpose it to 200. So we perform source NAT on the packet, and the source gets transposed to be that. In addition to that, my blue rule here is going to affect the destination. So my on-prem device sent it to 100.0.0.4, but my VPN gateway blue rule is going to transpose that destination, effectively perform DNAT, and transpose it to 172.16.100.4. That's the output packet when it leaves the NAT rule block on the VPN gateway. VPN gateway now drops the packet on the wire, destined for 172.16.100.4, and Azure routes it, effectively goes across VNet peering and gets delivered to my spoke virtual machine. My spoke virtual machine, as we saw with the TCP dump, receives a packet because it's destined for it, and it's sourced from this range here. It will respond, and it will respond to the 200 range. Now the source becomes, let's change this to orange. This is the reply packet. The reply packet now gets routed. The spoke now has a route that says any traffic going to the 200 range, go to the VPN gateway, and that was injected dynamically when we instantiated our NAT rules. VPN gateway gets the packet. Again, it enters the NAT rules. The source gets flipped and the destination gets flipped. Packet travels along the IPsec tunnel, hits my on-prem device, and the on-prem device says, oh, okay, I need to deliver that packet to my host with the 172 address, and it's returned to the on-prem client, source from the 100 range, and that makes sense to the on-prem client because that's where it originally sent a packet, and everything works at the networking layer, and we deliver the website to the client as expected. It's worth mentioning that if you want to have a look at the NAT metrics on the VPN gateway, that's exposed in Azure Monitor. So we see here we got the VPN gateway in Azure, metrics blade, various things relating to NAT packet drops, total NAT flows, total NAT packets, etc. So if I look at total NAT flows here, I can see that there's definitely some processing happening here in respect to NAT, which is what we would expect because we know our website's working. Okay, let's switch gears for solution option number 2. Probably you're familiar with something called Private Link on Azure. And one of the things we've highlighted in previous videos is you can use these things called private endpoints and ride the private link technology to get to Azure PaaS services, but also to get to this thing called a private link service, which can live in another VNet on Azure, and you don't need any sort of layer 3 connectivity between the consumer side with the private endpoint and the provider side with the private link service. You don't need VNet peering, you don't need routing at all. The Azure SDN magic makes this happen. And this is what's been shown in this diagram here, kind of come in over here, go to private link service, go to a standard load balancer, get to my backend. And you can see that even the on-premise sites that are connected via express route can leverage that private endpoint because it's just a NIC in the VNet, it's a routable IP address. One of the things that's sometimes missed when we dig into the use of private link service, it doesn't even matter if this virtual network address space on the left overlaps with the VNet address space on the right. And even if your on-prem address space here on the left, to kind of think about the left-hand side here as a common layer 3 routing domain, perhaps for your customer, it doesn't matter if any of that IP address space overlaps with the provider side. That's one of the kind of cool things about private link, because it happens inside of the Azure SDN. The actual IP addresses that are used in the overlays for each customer are irrelevant. They can be overlapping. And we can use that behavior of private link service to also address this overlapping scenario. So let's jump back to our diagram to show you how that's going to work. Okay, so we've still got our spoke VNet at the top, exposing the application now that's hosted on Azure that needs to be consumed by another third party that happens to have this on-premises address space that overlaps with me. Okay, and that's the blue box here. I've configured a standard load balancer in front of my web server, and I've mapped that standard load balancer to a private link service. And I'll show you what that looks like in the portal in a second. The next part of the puzzle here is, well, how do you get to that private link service? You need to get to it from a private endpoint. And this is the cool thing with this solution is this private endpoint can live in any VNet anywhere, owned by anybody on Azure. So this purple box here, it could be your VNet, as in the blue provider side VNet, if you wanted it to be, and you could still set up that IPsec VPN to your third party. Or you could say to that third party, the red people here, hey, if you're already in Azure, if you've got an express route connection to Azure, or you've got an IPsec connection into Azure, or maybe you say to them, hey, just build an IPsec connection into a VNet that's completely isolated under your control, then you can leave all of that to them. So this purple box here can kind of be owned by anybody. In my scenario, I'm going to imagine that it's owned by the red party. So they've got a pre-existing connection into Azure. You can see here they've got a VNet in Azure with this 10.249 space, and they've got the 172.16.100 range on-prem, which again overlaps with this blue provider side that they want to ultimately get to on Azure. So very simple configuration, simple standard load balancer with an internal only front end. So I've statically mapped the front end. Backend pool, single backend pool, has to be defined based on NIC when you're using private link service. You see my backend there is pointing to the NIC on my spoke virtual machine. And I got a very simple health probe. Hey, just check it's alive on port 80. My load balancing rule is equally simple. It's just take it in on port 80 and spit it out on port 80. In the blue box, on the provider side, I've also built a private link service. I've given it a static IP of 172.1600.75. Remember that, that's important, that's the NAT IPs. So when traffic comes into my backend app later, you'll see it actually originating at a IPv4 perspective from this NAT range. Notice I've got an alias here that represents my private link service. I'm going to copy that. I need that in a second. You can add more IP addresses, either statically or dynamically, to this private link service object. And there's some documentation around when you need to do that in terms of scale, snap ports, etc. Okay, so that's the blue box. That's the provider side, the application owner side. We'll jump to the pink box now, and this is where we need to set up that private endpoint and link it to the private link service. Create a private endpoint, give it a name, and straight away it says, where do you want to connect to, right? That private endpoint can go to a PaaS service and go to storage, SQL, but I want to connect to a resource by alias, and I've pasted in that alias that was given to me by the people that manage the blue box. I'm going to put it inside of this 10.249 space inside of my purple box here. So that's where the private endpoint NIC will get instantiated. Let's kick that off. So the portal at the moment effectively is bridging the link between this private endpoint across the Azure SDN into the private link service. We said that's mapped to the standard load balancer, which has rules that steers the traffic to the NIC on my backend with that web server running. Notice that when the private endpoint gets deployed, it sits in a pending status. This is effectively waiting for the people that manage the blue box to approve my connection. And we'll see that here as the connection state pending. You just select that and approve it. Back on my on-premises VPN device here in the red box, notice now that we've reworked our lab. I'm no longer getting any of those 100 addresses. There's no NAT config in place on the VPN gateway anymore. As I said, this could equally be ExpressRoute or any pre-existing connection to Azure. No NAT config, and we're not getting the 172.1600 range via BGP, but we are getting this 10.249 range, which is my address space within which my private endpoint is located. So I've got layer 3 reachability from the red box to my private endpoint. We can see here that my NIC, my private endpoint's got the IP address 10.249.249.4. If I log into my on-premises machine here, it's red VM down on-prem, I've got an RDP session open to it here. If I target that private endpoint address, I get back my Apache page that is running on the web server hosted in the blue box. So again, just to bring it home, let's do a packet walk. The virtual machine on-prem sourced the packet from itself, 172.16.100.4, and it was destined to 10.249.249.4. So we told our on-premises team, hey, use this address to get to this service that you ultimately want to connect to. There's logic on premises that routes the 10.249 range to the VPN firewall. Again, as we said, could be ExpressRoute or whatever hybrid connectivity that Red partner has in play. The VPN device then routes that traffic over the tunnel because it's destined for an IP address inside my VNet. VPN gateway gets the packet, no NAT involved here at all, and then sends it to wherever the Azure SDN tells it to, which is the private endpoint, of course. The private endpoint gets a hold of it, and that's when private link kicks in and says, okay, what's this private endpoint actually used for? And we know earlier we mapped it to a private link service. It goes across the Azure SDN. Remember, no layer 3 routing, no VNet peering at all. Could be a completely different tenant, and enters this private link service here. At that point, the source address is changed and it's NATed to 172.16.100.75, which is the NAT IP of that private link service in my VNet. Between the private link service getting a hold of it and the SLB doing some magic, the destination address is ultimately rewritten to be 172.16.100.4, which is the VM NIC associated with my backend web server. So the packet looks like that when it's delivered. Again, we can verify that pretty easily by kicking off a TCP dump on the backend blue web server, looking for traffic coming from the SNAT range of my private link service. Go back to my client and refresh the website. Straight away you see traffic coming from the IP address as we described earlier. Okay, I hope you found that useful. That's two possible ways to overcome overlapping IPs when you're working with partners on Azure. Now, the possibilities here are endless. Really, my goal here was to highlight another tool that you should think of having in your toolkit as a network architect working on Azure. This could apply to scenarios where you acquire companies. It can work between VNets in Azure. It can work between companies that are hosted in Azure. Like, yes, we've used the on-premise scenario here, but don't let that bound your thinking. These technologies and solutions we talked about are useful in many scenarios. So just to recap, we had option one there, where we ultimately used the NAT function on VPN Gateway, and that's also available on the VPN gateways inside of Azure Virtual WAN, if you're an Azure Virtual WAN customer. And then we looked at this ability to also use Private Link and Private Link Service to abstract away the actual IP addresses and make this overlapping scenario work as well. Which one you choose probably largely depends on the use case. I think if you're already working with a third party that's in Azure already and they've got a presence, they've effectively got a purple box, you can make a very good use case for Private Link Service. Pretty simple to set up. I'd say where Private Link Service also works better is where you have very prescriptive ports, right? Remember, in this flow, there's a load balancer involved where we define rules, etc., based on ports. So anyway, I hope you found that useful, and I'll speak to you in the next one.